Morning, everybody. How are we doing this Monday? So. Yeah, I've already heard that some of you have a big week of tests. Well, at least my 4A students. Do you guys have tests this week?
Yeah.
Math. What exam?
Circuits.
So study hard. To add insult to injury, next Monday you get to come in an hour early.
Oh yeah. That's right.
Okay, spring forward. That happens this weekend. Okay, so just preparing your minds and your blood pressure. You know, there's more heart attacks on the Monday after something like a 12% increase in heart attacks, 13.5% increase in vehicle accidents on that Monday. So please be careful. We do have a visitor today. Shirley McManus, our dean, is here to make sure that I'm doing my job. Any complaints that you have about my teaching, you blame her, okay? Because she was one of the 6 people who hired me 22 years ago. Yeah, okay? And there's a story where I almost fell in her lap off of the table as I was demonstrating Newton's third law. So maybe you can ask her about that sometime. Always leave an impression, right? What I did ask for permission to jump on the table from the chair of the committee at the time. What he didn't know or failed to tell me is that the leg of the conference table was broken. So when I did the standing leap from the floor to the chair to the table to demonstrate Newton's third law, the whole table shifted, and Shirley was in the landing zone. I did catch the overhead projector though. That didn't crash to the ground. I put up a, the other person you can blame, by the way, is Mr. Glaze. If any of you have had Mr. Glaze up at...
he's our circus teacher.
Yeah, your circus teacher. You can blame also.
Right now.
He was also on my hiring committee, so you can blame him.
Yeah, he's amazing.
Yeah, he is amazing. Anyway, I did put up a link to the, remember the poll everywhere thing we did in class? I had you guys test, where you could ask questions, all kinds of stuff. I put a link up to one that supposedly you can use at any time. Right? Like if you have a question you want me to answer at the beginning of the next lecture, you can hit that link there. I checked today, nobody's asked any questions. Okay? So it's not one of those anonymous things, right? So you can ask whatever you want, be decent, right? But I can go in there and see if you have questions, and then we can talk about it in the first few minutes of class, whatever, right? Or you can ignore it, right? It's a test, right? I'm testing the software that they've given us access to, but it's right there on the front homepage. I put it up last, I don't know, Thursday or Friday, and none of you looked at it, so I can see exactly how many of you actually look at the homepage. All right. So what were we doing? We were in the thick of lenses, weren't we?
Ray tracing.
Oh, ray tracing, that's right. So, what I have to give you, okay, I have a present. Where did my present? Right here. Okay? So what I want you to do is I'm going to pass these back, right? Take one. Should be enough for everybody. Okay? This is what we call paper. I know, it's like amazing, right? And I know it's on the screen, okay? And I know you have the capacity to write, okay, in your notes, but I wanted you to have a physical thing, okay, so that you could reference. You're going to need this over and over again, okay? So I wanted you to be able to reference it, okay, right here today in lecture. You're going to want to carry this around in your notes and have it with you while you're working the homework, okay? You're going to want to put this on your bathroom mirror and stare at it every day because you will live and die, okay, by the sign conventions that we use in optics. We have a lot of these conventions. Like, where do we measure the angle from in optics? It's from the normal to the surface, right? It's not from the surface, which is already weird enough. But what this sheet represents, do you remember back in 4A when I was always on you about coordinate systems and which way is positive and all that sort of stuff? This is the coordinate system for optics. This is it. It's predetermined, and it's called a convention because in optics we've all agreed that we will use these terms and these signs for these terms and all that sort of stuff. So have this ready to go. I have it on your summary sheet, your cheat sheet, right? Upcoming exam. This, I guarantee, is where you're going to make mistakes. The math is not going to be hard. You've done harder math. It's getting the signs right on stuff where you are going to kind of run afoul of things. All right. So last time, right, we were kind of playing around, okay, with these mirrors. And I want to give you the mathematics, right, of the images that we see. So let's review real quick what we learned last week. How do we describe images in mirrors? Like, there's kind of three ways that we talk about it. Virtual. Okay, so there's virtual or real. What's the test? Like, how do you know if you got a real image?
You can block it.
You can block it, right? You can interrupt the real physical rays that are present, right? So where are you seeing the image here? Is it kind of back here maybe a little? It looks like it's inside the mirror, right? Okay. Are there any real physical small people on the other side of this? No. Okay. So what kind of image is this?
Virtual.
Virtual. Now, it can be very difficult to tell the difference between a virtual and a real image. You're going to find this out tomorrow in lab. Okay? Because we're going to expose you to virtual and real images, okay? And how you can tell the difference and all that sort of stuff. But this is a virtual image. Okay, what's another way that we describe an image?
Magnified or reduced.
Magnified or reduced. So is this magnified or reduced? Reduced. The things look smaller than they would normally. Okay? And then the other way? Upright or inverted. And what's the way on here? Upright. Things are the right way. Okay, they're not standing on their heads. That sort of stuff. Okay. So as you can see, that language is in the sign conventions, right? Okay. Do you see how we have upright or inverted down there for magnification? How do we go about solving for these things? Well, there is, of course, equations that govern the physics of what's going on here. And I'm going to give you the two main ones. And there's variations to this equation. It's all the same equation with different symbols. I'm sorry, just optics is a little bit screwed up that way. Here's the one that I like to use. It gets a little bit upset sometimes. Thank you for letting me know. Is it going to let me? Okay, I need 1 minute because what has to happen is a little bit of a reboot. Anybody see any good movies this weekend? You did? What'd you watch?
I don't know if it's good, but I watched Cookie Bears.
Everything that's wrong with America in one movie.
But it's based on real.
It's based on real. Guys, before Cocaine Bear got famous, you see the bear that was like taking selfies at there was one of those cameras that they set up, and right, the researchers had set up, and this bear found the camera and kept coming back to it night after night after night, and he would play with the camera and do all that. Just give bears cell phones. Why not? It just, it should work. All right, let's see if this works. Okay, so back where we were. We have 1 over the distance to the object. We have 1 over the distance to the image. And then we have 1 over the focal length. Those of you in 4B are starting to have post-traumatic stress when it comes to finding the distance, right? So there's a lot of 1 overs in here, right? So you're going to get really used to that key on your calculator that's like the 1 over x button. Okay, right? And I'll define what these distances are here in a second. But there's that equation that governs the relationship between all of these things you see in the sign conventions. And then there's the magnification equation. Okay? And the magnification equation is negative the distance of the image over the distance to the object. So these two equations will be the equations that we use when we're working in optics for figuring out where images form, what kind of images they are, etc. mathematically.
Oh, you say that.
Is the focal length. So let me try to give you some idea here, right, about how we measure these distances and where ray tracing and ray tracing diagrams come in. I already told you I'm kind of changing things up a little bit, and I'm not going to be making you draw ray tracing diagrams. The reason being is that they're all in the book already, and there are too many good things, too many good resources out there for having it done for you, actually. So let me show you, at the risk of breaking everything again, let me show you, I put in the modules, right? So again, for all two of you that are actually paying attention to what's going on Canvas, in the module for optics, okay, I put two links in here, smaller, okay? Mirrors, ray tracing, diagram simulation, and one for lenses, okay? These are links that will take you directly to a simulation. Let's do the mirrors one, okay? So here, this is an interactive ray tracing diagram for figuring out what's going on with, in this case, a concave mirror. And the way it works, can I zoom in on this one? Look at that. I want to dismiss you. Okay, so they've drawn the mirror for us right here. Notice how in this diagram there's this horizontal line that it's charting out distances for us. That horizontal line is called the optical axis. You always take sort of the midpoint of your optical element, in this case a mirror, and you cut it in half, and that becomes your optical axis. They've labeled for us the focus, the focal point of the mirror. And again, that focal point is determined by the curvature of this mirror. So the center of curvature, which I talked about last time, gives us like the center of the sphere for this type of mirror. And that focus is half of that. So there's the center of curvature right there. And there's the focus. You can see it's not quite to scale because this thing looks like a much bigger sphere, doesn't it? All right. But notice how the software is drawing a ray. This ray comes along, parallel to the optical axis, bounces and goes through the focus. By definition, that's what the focal point is. It's the point at which all light, if it comes parallel to the mirror, will be directed towards that focus. We've got our object, okay? And there's another ray that comes from the tip of the object through the focus, strikes the mirror, and goes parallel to the optical axis. And then there's another one that goes from the object through the center of curvature, and in this case doesn't intersect the mirror. So back in the old days when we actually had paper and rulers and pencils, we would do all this. We'd have you draw these diagrams with a ruler, right? Parallel and bouncing off and all that kind of stuff. Well, we have the internet now, right? Okay, so you can just grab the tip of the object, okay? And you can change its height, and you can also change where it is, okay, in relation to the kind of key parts along the optical axis, which would be like the focal point and all that kind of stuff. So if I'm way outside the focal point, okay, it's labeled the image for us right there. What can you tell me about that image? What's its orientation? It's inverted, right? It's upside down, right? The arrow started pointing up and now it's upside down. Magnified or reduced? You can see that it's smaller, right? So it's gonna be a reduced thing. Real or virtual? It's real, okay? There are real rays. All three of these rays come off, and all three of them converge right on the tip of that object. So what you're seeing here is the very basics of what Pixar does whenever they want to animate a movie. Okay? This ray tracing, the mathematics of this starts very simply with the equations I've given you and eventually becomes much more complicated when you have a three-dimensional surface and all that sort of stuff. But Pixar takes what the artists do in their design software, translates the modeling and the texturing and the hair that they put on the characters and the way they want the characters to move, and then the render farm, when all the artists go home for the day, the render farm runs all night rendering the frames, and it does so by ray tracing, by taking these rays of light and calculating how they interact with surfaces and what all those reflections are going to be and all that sort of stuff. Monsters University was the first film that Pixar ever made that was completely ray traced. Like every single frame, every bit of light, all was calculated via ray tracing. Before that, they would use other methods and they might sneak ray tracing in here or there. So Cars, the first Cars movie, was the first one where they used ray tracing to get all of the correct reflections off of all the chrome pieces of the cars, right? And so they used techniques that didn't require a lot of computing horsepower, right, to get most of the frame. But when they really wanted a good reflection off the cars, headlights, or whatever, right, they would use ray tracing. Monsters University was completely ray traced because at that point the computers were powerful enough to be able to do all the calculations for everything in the scene per frame. Nowadays, you can go buy computers with graphic cards that can do that ray tracing in real time. Fast enough so that the game can run at 30 to 60 or 120 frames per second, and you get accurate, detailed reflections off of surfaces within the gaming environment. Okay? So whenever they're talking about, oh, this game supports ray tracing, okay, this is it. This is the beginning of it. It does get, of course, very complicated when you've got tens to hundreds to thousands of light sources that you have to trace those rays. But anybody that's ever played Minecraft knows when you see Minecraft and ray tracing, you know you've arrived. All right, so you can do, so there's like, you want to focus on different regimes here. By the way, the distance to the image, the distance to the object is always measured from the vertex. The vertex is the point where the optical axis crosses whatever, your mirror or your lens. Okay? So this is 0. You can see they labeled it 0 right there. Okay? The focal point, they say -4, but the one thing that this thing does wrong is that it doesn't give. They're sticking this axis right here as like a x-axis. The front side of your mirror is always the shiny side. And if you look at the sign conventions, what does it tell us? The front side is always the positive side. Okay? And I think I could probably flip this thing around. I probably didn't set it up correctly, but that was the one mistake they made in their labeling of their simulation. But we can see the focal point is 4 centimeters. I think everything's in centimeters here. Not given. It's got to be a mathematician that did it then. Right? -8, so on and so forth. Okay, so if I take and grab this object and I move it, notice that when it gets to the center curvature, I get sort of a 1-to-1. What do you think might happen if I put the object on the focus? Remember, the focal point is where all the rays coming parallel would converge. So it shoots back. And we talked about this in the context of headlights, right? Okay? How you put the filament right at the focal point of the, right? So that everything comes out parallel. You can see those beams are coming out nice and straight and parallel to each other, right? Except the one that's going down, which is weird. And then, look at that. As soon as I go on the other side of the focal point, what happens? Oh, those dotted lines come out, don't they? And again, those dotted lines are the lines that your brain is following backwards, right? Your brain is insisting that the light is coming, that light travels in straight lines. And so your brain traces back the origin of where that light came from and constructs this virtual image where? In your head. It's showing up behind the mirror, but really this image is forming in your head.
So is there like a ratio that's close enough for like to human eyes, but human eyes see?
Okay, so we're going to talk about lenses here in a bit, because for our eyes it's all about lenses, right? We're introducing it to you as mirrors to begin with. All right, and then there's a way in here to flip this mirror. Oh wait, no, maybe it's just this. There you go. Okay, so if I have the object on, the shiny side, okay, and it's concave. How do you remember when it's concave? I'm exaggerating here, right? But Cocaine Bear has to walk into the cave. Right? And then if it's convex, it's just the other way around. And what's the front side?
Shiny side?
The shiny side. Right? So I could reverse these drawings, right? It wouldn't matter. Okay, but to get this to be the convex mirror, I just grab my object and slide it over. And there's nowhere over here that you can put this thing, okay, and get a real image to form, right? Everything's always virtual. Okay, so let's do some examples where we're working with the math and sort of the drawings. You want it, now, are you allowed to have this on the exam? No, right? Okay, you're not allowed to have this on the exam. So I'm teaching you how to use this thing, and then I'm just going to rip the rug right out from under you during the exam. Good luck. Yeah, so you're like, yeah, that's exactly what you do, Mr. Bailey. Like, experience it every time. What are you going to do?
Scenarios.
You're going to put little sketches, right, on your summary sheet that you can reference. So let me show you how I would kind of go about doing this. We need, I'll just do it here. All right, I do have to blank that out to make this work. So let's just do, let's say that you're given a problem where you're told that the focal length is plus 15 centimeters. So what do you instantly know based on the sign conventions? Look at that sheet I gave you. Okay, the focal length, which is F, right? Being positive means that the focal point is on the front of the mirror. How is that possible? Well, you draw an optical axis. You draw a mirror, okay? Just sketch it out real quick. Doesn't have to be pretty. And so which side of this is the front? Where is the focal point of this mirror? The left-hand side or the right-hand side? It's on the left. It's somewhere over here, right? Because it's curving towards that thing. And so if we have a positive focal point, it's on the front side. And by definition, the front side of a mirror is always the side that the object is on. Otherwise, can I see me? Right? That doesn't work, right? The shiny side's on this side, so all the objects always have to be on the front. So you're like, well, Mr. Balogh, why have a sign convention that says a negative object distance? Right? If the front side of the mirror is always the side that the object's on, it's always going to be positive. I have a negative one. We'll find out. You'll find out. Later. All right. So we know, because they told us it was a positive 15 centimeter focal length, that the drawing has to look like this. That's the first thing we know. Okay. If they told you it was a concave mirror of focal length 15, now what do you have to do according to the sign conventions? Concave mirror of focal length 15. You have to put a plus sign on it. Because the only way that the focal point and the object can be on the same side, okay? But what if they told you it was a convex mirror of focal length 15? Physics textbook authors love to do this. You've got to stick a negative sign on that focal length. Why? If this is where the object is and this is the shiny side, where's the focal point for this curvature? It's over here. It's on the back side. And according to sign conventions, what do you do if the focal point's on the back side?
Negative.
Negative. Where are you going to mess up in these problems? Signs. Right? Okay, you're going to mess up on the side. Okay, so we're told that focal length. We are told that the image has a height of 10 centimeters, or the object, sorry, has a height of 10 centimeters, so the actual physical thing. And then we're also told that the distance that the object is placed from the mirror is 40 centimeters. All right. The object always has to be on the front side of the mirror. So what sign do we give that object distance? Which side is it on? It's on the front side. So we're going to give it a positive, right? You're going to want to be very careful about your signs. Always explicitly state your sign. Positive or negative. Even I know, positive number, let's put positive. Put positive on it. When you go back later, day later, try to figure out what you did, why did you choose it, you're going to want to see that you thought about it, right? And that you put a positive. And And maybe you did it wrong, but at least you know that you, at some point, tried to decide. All right. So, a little tiny sketch, right? If this is my focal length, my object, right, is going to be outside that focal length, okay? So I could hop on the link that I showed you and set up a little situation where this thing's going to be outside, right? Just to get a visual for what's going on. Or I did show you and put into the notes this picture, which looks overwhelming but does contain all four of the possibilities really that you can have, right? So what possibility are we in with our example? Yeah, we're in the top. See how the object is way outside the focal length, right? 40 centimeters versus the 15 centimeter focal length, right? So that's sort of the picture here. And I can tell right from the picture, I should end up with an inverted, real, reduced image, right? Just by looking at the ray tracing diagram. So again, have these pictures available to you so that you can reference them as you go. Okay, so that's kind of what my picture is going to look like. And we're going to solve for image distance. We're going to solve for everything that we could possibly try to find out about this thing. So again, the operative equation is it. Oh, by the way, I forgot to warn you. You will see in various textbooks, websites, YouTube videos that you might go, you might see this. 1 over P plus 1 over Q equals 1 over F. P and Q was a standard for or object distance and image distance since really optics was invented way back when. Okay? I don't know why. I have no idea what it has to do with the idiom mind your P's and Q's, right? But this was object distance for some reason, and this was image distance. I hate this. How many times have I flipped this? All the time, right? Okay, it doesn't make any sense to me. Which is why I've adopted the more modern notation. I have seen this in some newer textbooks of distance, d sub o, distance to the object, right? D sub I, distance to the image. How dare I try to make physics clearer? Come on. What am I solving for here? What's the thing I don't know? Image distance, right? So to solve for that image distance, I have to move over my 1 over DO, and then as a final sort of thing to do in my calculator, I do have to invert, right? Everything like that. So my image distance will be 1 over, what did I say, 15, positive 15, minus 1 over positive 40. And then I invert that whole thing, and when I do that, I got 24 centimeters. So I came out with a positive sign for my image distance. What does that tell me? According to the sign conventions, what do I know about where this image is forming? It's in the front, right? Because if the distance of the image is positive, it's on the front side. What if the problem gave you the image distance and asked you to solve for the object distance? What do? Same thing, it's just your known thing is now the image distance, right? Okay. Or maybe the problem gives you object and image distance and asks you to find for the focal length. Is the actual algebra hard? No. It's getting the signs correct and how the signs relate to the conventions and the pictures, the ray tracing diagrams, and the simulate, or if you're using the simulation, right? Okay. How that all kind of comes together, organizing your information and having the conceptual framework correct. Okay, knowing that I got a positive image distance means it's on the front of the lens, which I'm not surprised about because up there in the top left is that image on the front side of the lens. Yep. Okay. I can solve for magnification. Now that I have the magnification, it was negative image distance over object distance, so that's negative of a positive 40 over a positive 24. How easy is it to get the wrong numbers in the right numbers in the wrong spot? Very. Okay. And by doing that, I got negative 0.6. Ooh, okay. According to the sign conventions, what does a negative magnification mean?
Inverted.
It's inverted. And was it inverted in the picture?
Yes.
Okay. What's the 0.6 mean?
Smaller.
It's a magnification factor. So anything less than 1 means it's reduced. Anything bigger than 1 would be magnified. So, to describe this thing, okay, I would say that it is a reduced real inverted image. There isn't an order that you should do that in, right? It's not like you say, is it real or virtual first or anything like that. But you communicate, right, using these words, what the image is. Yeah.
Will we only know whether it's real or virtual based on the schedules we put on our sheet? There's no other way to do calculation.
Okay. I'll level with you. I know you want me to give you a surefire way from the math, right? To know whether or not an image is real or virtual. It's not that simple. After you've done this for a long time, can you get like a sort of an instinctive feel for what's, yes, okay? But I've literally been over thousands of ray tracing diagrams and very complicated systems. And my master's degree is in optics, right? Like I specialize in this. So can I sit down, look at it real quick and go, yes, okay? For you, do not fall into the trap. So there's a lot of times students, this is the trap. Oh, I got a negative image distance, therefore it must be virtual. No. Think about what negative image distance means. It means that this thing forms on the back side of a mirror. That's what the convention says, right? Back side of the mirror. And if an image is forming on the back side, is it possible for it to be real? No, in a mirror that's impossible. But we're about to transition into lenses. And what do the conventions do? Look just down at the bottom half.
They flip-flop.
They flip-flop. And this is where you will mess up. So, for a mirror, if you're on the back side, 100% guaranteed it's a virtual image. But for a lens? So I would rather you stop to think about and look at the picture, look at the simulation, right? To determine what's going on. So let's do an example here where we do have a virtual image. So this is a convex lens, mirror, with a focal point of 15 centimeters. So if it's convex, what's the picture? It's not a cave, right? It's the Audi belly button, whatever. Okay. So that's kind of the picture that we have. Little sketch can always help orient you, right? Where's the focal point of this mirror? Stop. Where's the front side of this mirror? Why is it on the left? Because that's where the object is, right? Front side is always where the object is. So there's the front side, okay? So here's the back side. This mirror is curving away from the object, so the focal point has to be over here on the back side. So what are we going to do with our 15 centimeter focal length? Why is it going to be negative? Look at the sign conventions, right? Okay. If the focal point, yes, is on the back side, then we've got to give it a negative focal length, right? Negative 15 centimeters. So key. We'll do a height of 10 centimeters again, and this time we're just going to put it at an object distance of 20 centimeters. So let's go find the image distance, right? So similar to before, it's going to be 1 over f minus 1 over distance to the object. I already did the math here, right? So I'm not going to do it again. And so that's 1 over a negative 15 minus a 1 over a positive 20. And all of that gets inverted to give me a negative 8 point, just call it 6 centimeters. what does that negative sign on our solution mean? Look at the sign convention. Don't guess. Look at the sign convention.
It's on the back.
It's on the back. A negative image distance means it's forming in the back. Okay, so let's see if that jives with what our simulation or our pictures tell us, right? So which picture is this? We had a focal length. We had none of these. There we go. Because there's only one picture for a convex lens. Okay. So we have object. Where is the image forming? It's forming on the back, isn't it? And from the picture, you can see it's a virtual image and it's upright and it's reduced. Okay. So this is the picture with too many rays drawn. Okay. If we're doing the simulation. Okay, I've got my object right here. Okay, I'm over here on this side. I know it's backwards from the drawing I've got, but you see, no matter where I put this thing, right, there's no changing or flipping of anything, right? Okay, so I'm always getting that virtual image, no matter what. It always seems to be reduced, okay, and it does always seem to be upright. Okay. So I'm happy, right, that negative sign did crop up in my mathematics. Because it's telling me it's forming on the back side. Let's see what else we can determine. Magnification. Negative image over object. So that's a negative times a negative 8.6 all over a positive 20. So what kind of number am I going to get out of this? This is a positive number. And what does the sign convention tell us about a positive magnification?
Upright.
Upright. I got 0.43, right, for that. No units. You're dividing a distance into a distance, so magnification factor is unitless, right? So what does that number being less than 1 tell me? It's reduced, right? And if it was 10 centimeters tall to begin with, how tall is the image now? 4.3 centimeters, right? 10 times 0.43. So we can find out a lot of stuff. And it's upright, okay? It's negative image distance, and from the diagram I would conclude that I would have a virtual image because it was forming on the backside. Is anything that we've done today hard? Is putting everything together difficult?
Yes.
To get correct? Yes. Right? So all the individual pieces not terribly difficult. Like the math here is right? But the struggle is making sure that you do the due diligence in the concept to nail those signs. It's practice, right? Make all the mistakes you can before you get to the exam. Now that the dean is gone, I think. Yeah.
Good.
Was it any different from normal?
No.
No.
A lot of teachers act different.
I know, I don't care. I do care. Shirley is the best dean I've ever had, and I don't say things like administrators are good, but she's good. You guys don't know. I can say this now that she's gone. The fights that she fights on your behalf on a daily basis. It is. I have stories. Okay, right? It's amazing, and by and large, the faculty in this division are really student focused. And it comes because we have good leadership like Shirley. So, I always enjoy having her in class. I wish that she would come more often, but she is very, very busy, and I look forward to what she has to say. She's always got good things, critiques and things. It's not like, oh, you're amazing. It's like, hey, have you tried this, or this was this. She's a biologist, right? She had no idea what we were talking about, and maybe I taught her. We'll find out. All right. And please do, apparently you're still getting emails even if you did the survey, so I don't have any control over any of that. But if you will please do the survey, take one, pass the box. If you haven't, I did get a report that just said like a percentage of the students that have done the survey in my classes, and you guys are hovering around 50%. Right, so please, like, just put peer pressure on each other. Right? Hey, did you do Mr. Bills? Right? Because for me, over 90% students take it tells me that I've got the full spectrum of everybody's experience. So let's face it, what students are really going to go do a survey? If I ask them. Either the ones that really, really like it or really, really hate it, right? Because they have a chance to complain or, oh, I love it, right? I want the whole spectrum, as much data as possible. That's what's important. All right. Oh, and spoiler alert, they're not going to fire me.
Even though you're leaving us,
What's that?
even though you're leaving us for 2A.
That's not my fault. Well, kind of is. I mean, I agreed to it, but it's a good thing. It's a good thing. All right, let's do lenses. So, when it comes to lenses, that's a mirror, that's that. Thin lenses. Okay, so when it comes to lenses, we are going to, we're going to do spherical lenses, first of all. We never do any other geometry other than spherical or flat. The other thing is, we are going to assume that our lenses are thin. And by thin, we mean we don't have to worry about, like, if the lens is too thick, what the refraction angles and things that are going on in the material itself. Basically, a thin lens is just two surfaces, right, where light is refracting. And you can imagine it could get pretty dicey if we had to actually, like if you got a lens that's curved so it's convex on both sides, right? Imagine like having to come in here and then right here having to do the refraction angle, right? And then because the curvature has changed and the normal is different here, having to do another refraction angle, right? Like it can get really hairy really fast, right? Especially as you stack up different surfaces in there. So the thin lens simplification does two things. Number one, makes it easier on us. And number two, works really, really well for everything. Like it's amazing how well the thin lens equations work for real everyday lenses in cameras and cell phones and all these kinds of things. You really have to be doing something super exotic to have to go in and actually do the raw ray tracing and everything for the system. So this is actually a really good simplification that works in quite a few places. But you'll notice that there are some fundamental differences in the conventions, right, that we use for the signs. The thing about a lens is that it's two curved surfaces that we have to deal with. The mirror is really just the one side, right? Whatever happened on the other side wasn't important because there's only one shiny side. But in the case of a lens, we're going straight through it. And so lenses have two focal points. Right? There's a focal point for one surface and a focal point for the other. Here I drew a converging lens. This left-hand side of the lens. Where is this left-hand side's focal point? Look at the curve.
On the right.
It's over here. Okay? And the one that's on the right, its focal point's over here on the left. But what if I had, say, a diverging lens, which looks like that? Again, it's a lens, it has two focal points, but where's the focal point for the left-hand side? It's on the left-hand side. Where's the, on the right? And what happens if I give you something like this? Two focal points on the same side, right? So we're going to limit it really to converging, pure diverging. But it turns out the thin lens equation works for all three of these cases. I'll show you how. Well, actually, I won't show you. It works as long as we are consistent with the choices that we make about the signs that we put on things. Okay? The ray tracing diagram for these lenses are actually fairly simple. Again, there's these kind of three rays that are always representative of what the object and image are doing. But what kind of image do we have over there? Real or virtual? It's a real image. See how the real rays are present? You can tell in the diagram that they're real because they're not dotted lines. Right? So there's real rays present there, upright or inverted. It's inverted. Okay? And magnified or reduced. Looks a little bit reduced, right? A little bit hard to tell in their diagram, okay? So what I want you to do, okay, I've handed out these magnifying glasses for you, okay? And I want to take you through a little bit of an exercise so you can see what's going on here, right? So what we have are different cases. So really the two things that you can do with a lens is put the object outside its focal point or inside its focal point. There's really, those are the two regions or regimes, okay? So take the magnifying, I know a lot of you are going, oh, yeah, right, okay, we'll get there. I want you to take this magnifying glass and hold it at arm's length and look at something far away. Okay, maybe move it around a little bit, okay? And I want you to tell me what you see. First of all, upright or inverted? Inverted. Everything's upside down, isn't it? Okay. Magnified or reduced?
Reduced.
I mean, yeah, one looks a little bit smaller. Okay, right? So it's probably reducing a little bit. Okay. Real or virtual? This is real. I just showed you the ray tracing diagram for this. This is what, so the object that you're seeing is out there. So what's the front side of this lens? Is it the part towards your eye?
No.
No. The front side's always the side that the object is on. So where are the objects that you're looking at? They're way out there, right? Okay. So the light's coming through and is forming a real image somewhere in the space between this lens and your eye, and then your eye is seeing that real image, right, through this lens. So that's the ray tracing, right, and the setup. And it's hard to tell in my picture, but that's upside down, okay? So now what I want you to do is put the object inside the focal length of this lens. In other words, use the magnifying glass as most magnifying glasses are usually used, which is where the object is put pretty close to the lens, right? So hold your hand, look at your notes, do something, right? But now, instead of having an object that's really far away, we're going to have an object that's inside the focal length of this lens. We're putting your hand inside the focal length. So according to the ray tracing diagram, what kind of image is this? Real or virtual? This is a virtual image. So really, where is this image forming? In your brain. Okay? We can calculate where our brain perceives this thing is, right? But is it magnified or reduced?
Magnified.
Greatly magnified, right? Okay. Upright or inverted?
Upright.
Upright. So you got to experience the two regimes, right? A real image and a virtual one. And tomorrow in lab, we're going to give you an optical bench that allows you to very accurately measure distances and things like that, right? And you're going to be generating all different kinds of images and that sort of thing, okay? I'm going to send these back around and put them away in here. No, these don't go home with you. These are my magnifying glasses. I would start that in the middle, but it's in traffic management. If I'm doing the simulation, nope, come back here. There's another link right here, okay, to the thin lens simulation. So here's that simulation, right? And you can just grab the tip of the object and start moving it around. Notice what happens to the size of the image as the object gets closer and closer to the focal point. See how it's getting bigger? But it's still a real image, right? How does this image on this screen get so big when it starts so small in that projector? Physics. Right? What are they doing in that projector to make sure this image gets really big? Putting the object, which is the LCD little TV that's in there, really close to the focal point of the lens that's in there so that it can be a real magnified inverted image?
They inverted inside.
Yeah, the TV set is upside down. Exactly the button. You just say invert it, right? And actually, there's multiple elements. There's not just a single lens in there. There's several of them, so gotta keep track of all that.
So that image is real?
Yes. I can interrupt the light rays. This is a real image.
So at what point it becomes virtual?
What happens when you put a object right on the focus of a convex or converging lens? Yeah, the beams become parallel, right? So this is another way to project light out. We don't put lenses in car lights. They're more expensive to make. It's much easier to make a mirror. Okay? So it could happen. Okay? And now, as I transition to inside the focal length, what do we get? Yeah. So notice, outside, when you were holding it at arm's length, right? Object's over there, image somewhere over here. Now, when we go inside, where is the image compared to the object? It's on the same side, right? You're looking at your hand, right? And you see your hand over, the object's over there, but you also see the image over there, even though the image is in your brain.
So, like from that between the focal point is.
So out here, the image would be over here, and as soon as you get to inside the focal point, then the image flips onto the other side. I don't make the rules of the universe. I just deliver them.
So, but
Start doing what I was like, go ahead.
but how do you determine which one is virtual? Like can you just say it
You
again?
look at the diagram. Like I said, I know you guys want me to tell you the surefire way to always know if it's real or virtual. There's one way. If you can interrupt the physical rays, it's real. This will be you tomorrow in lab. You guys are going to be arguing, oh, it's real, it's virtual. Hold your hand up, put a piece of paper there. If the image forms on your hand, it's real. If you can't do that, it's virtual.
So, since there's a lens on there, if that instead of a projector was a camera and I was taking the image that way, would that be taking fake?
Cameras take real images. How do I know? The real light has to hit the sensor in the camera. A virtual image forms only one place, your brain. Okay? Cameras take pictures of real objects using real image, real light that hits the sensor.
So you use the camera on the magnifying glass, it would work?
It would. Oh, good. Yes, your brain just melted. I love it. I love optics.
So, like between a virtual and a real image, for all other animals, like other species, they'll see the same real image, right? But for the
Real light rays are hitting your retina. That's all. That's where I'm going to stop.
Okay.
After it hits your retina, I am not responsible. You have to talk to the biologists and the psychologists, because it's all about brain function at that point.
So it does like differ from.
Usually, animals don't wear glasses. I'm just also going to say that.
Maybe some of them.
Marcos?
So if it's like a double reflection, are those always virtual?
No. I know you guys want an island of stability, but the answer is you do the ray tracing. You do the ray tracing. It'll tell you. The ray tracing will tell you 100% of the time. Don't guess. Don't guess.
Follow the signs.
Follow the sign. There's a way on, how do I do this? Oh. Is it? Yeah, okay. On this simulation in particular, you have to drag the focus across to get it to become a diverging lens. Okay? It's just the way that they programmed it. This is a converging lens. How do you know this is a diverging lens? Look at the shape. Okay? And look at the focal length. What happened to the focal length number when I changed it to diverging? I go back to converging. What's the focal length? Positive. Look at your sign conventions. Right? Okay, a diverging lens will have a negative focal length. Okay? But notice, with a diverging lens, is there anywhere that you can put this object and get a real image? No. So like, you're guaranteed, if it's a diverging lens, for it to be what kind of image? A virtual image. Remember that. We're going to talk about this on Wednesday. Remember that the only image you can get with a diverging lens is a virtual image. Okay, that's not true for converging. For a converging lens, you can get both. And you just experienced both, right? With the magnifying glass, that was a converging lens, and it produced both real and virtual images. To mirrors, for the convex mirror, it's only ever virtual. There's no ray tracing that will ever give you a real image when you've got a convex mirror. But for a concave mirror, you can get both, real and virtual. So that's why I didn't want to give you like just a bullet, like it's always this. It depends. It depends on what surface you have and which way it's pointed and all that, right? Okay? But you can, with a diverging lens, it's always virtual. With a convex mirror, it's always virtual. Your brain is going to do some tricks on you. It's going to be, oh, every time I've solved 10 problems and every virtual image always had a positive magnification. Therefore, positive magnification always means, no, it doesn't. Okay? So don't fall into that trap. Look at the diagram. Okay, so let's flip this back. Converging lens. And let's do the math. Okay? I really did that focus way out there. There we go. All right. So this is like the one time that I needed like 4 projectors simultaneously, like 4 computers, 4 projectors, so I could show you all of that stuff. This diverging. Okay. Don't look. I didn't show you that. We'll stick with the sign conventions, but let's, on the sign conventions here, let me give you the equations. Okay? You ready? 1 over DL plus 1 over DI equals 1 over F. It's the same one. Okay? It's the same equation. As a matter of fact, magnification, also exactly the same. I forgot to tell you, magnification can also be height of image divided by height of object. So if they give you the height of the image, height of the object, you already know what the magnification is. Okay? And that one works for mirrors as well. I just kind of forgot to. I'm so steeped in optics, it's just sort of an automatic. I know what these ratios are. I apologize. So the equations are the same, which is, that's good, right? But not. Because the sign conventions are different. That key. When you're working with a mirror, you've got one set of conventions. When you're working with lenses, you've got a different set of conventions. So let's do some examples. Let's do this. Okay. So let's say that I gave you, I will just stick with 15 centimeters. because those are what I have in my notes. I came up with all these numbers because I used to do the actual ray tracing right on the board before we had computers. All right, so 15 centimeter focal length, okay, and I tell you it's a converging lens. So what's the first thing you know about like the sign conventions for the focal length? It's positive, okay. The little sketch, or maybe running the simulation that you want. By the way, thin lenses, the actual curvature in your diagram does not matter. For mirrors, it does, for ray tracing purposes. But the actual physical shape of the lens makes absolutely no difference because everything happens along a line along the lens. And so you'll often see me draw a lens diagram and never draw the curvature of the lens because it doesn't matter. But I'll try to remember to draw in the shapes for you. But I do have that midpoint along the lens always as a force of habit. Okay, so you're gonna have your two focal points, and when it says it's 15 centimeters from the vertex on both sides. And where's the vertex? It's that midpoint, right? Where the optical axis hits the midpoint of the lens. All right. So I got my focal point, and then I tell you that the object distance is 25 centimeters. So what are you going to put in for the sign convention for the object distance? Why is it going to be positive? What side is the front side of a lens? Opposite the back. The object has to be on the front side of the lens. Right? Otherwise, you're not imaging anything, right? Like, what are you looking at? So it's like, well, Mr. Balogh, why have a convention where the object could be on the back side of the lens? That can never happen. By definition, the front side of the lens is the side that the object is on, if you only have a single lens. They can switch around. Front and back doesn't always have to be left and right. In optics, we get really used to going either direction. Doesn't matter. One of the reasons I think I like optics so much is I'm dyslexic. And so left and right never made sense to me. Front and back, the side that the object is on, can be that way or that way or that. I don't care. Like, it's all the same direction to me. Okay. So I naturally clung to I'm like, finally something that speaks my language. Dyslexia. Right? That and the mathematics of optics is really kind of straightforward in the sense of it's not relativity. Or quantity. Okay. Lot of linear algebra, believe it or not, in optics. Some differential equations depending on what you're doing, but lots and lots of matrices to calculate out these things. Some really just kind of, dare I say it, really elegant mathematics, like just pretty. Just like, wow, like it's amazing that we can figure this stuff out and that it can turn into Sully from Monsters University. Anyway, Pixar started by hiring mathematicians. The artists came later because the mathematicians sat down and figured out how to do all the math of all the ray tracing for all that stuff.
Mr. Balogh,
Yes?
are you gonna make us use the cross again?
No. All right, so I know it's converging, I know the focal length is positive, and I know that my object is outside the focal length and it gets positive, which means by putting the object over there, this is the front side, isn't it? What if I wanted to draw my object over here? Now what side is the front side of the lens? And now this side is, so like, pick a side. Doesn't matter. The other side becomes the other one, right? So, and because a majority of the stuff that you will be doing will be single element systems, meaning a single mirror or a single lens, you're not going to run into a negative object distance. Okay. But it's in the conventions nonetheless, because why not? Let's see, what else did I tell? Oh, we'll just use an object height of 10 centimeters. It's easy to multiply again. Okay, let's find out where this image forms, like mathematically, right? Do the calculation. So, oops, 1 over di equals romping room math, right? Maybe not kindergarten. I was doing this in first grade. No, I wasn't. I couldn't even do. I was terrible at math. It's like 6th grade before I was even beyond fractions. I had a lot of catching up to do in middle school and high school to get to this point. It was not fun. But my 7th grade math teacher, in front of the entire class, told me that I would never amount to anything.
Ooh.
I should have sued. I could have been really rich. Right? No, she said because I was goofing off and just being an idiot and stupid. I was stupid. I was really dumb. And I wasn't nice to her either. She said she got frustrated with me at one point because I refused to do the assignment. Right, I had done 3 of my things. And I was like, I've got this, right? And she said, you'll in front of the entire class, you will not amount to anything if you don't learn how to work. She wasn't wrong, right? And I could have gone home, complained to my mom, and teachers meeting, which I did a lot anyway. But I have to thank her many years later, right? Because that was the moment that I realized if I want to fly, I wanted to like fly rockets and be an astronaut and fly planes and all that stuff. I really did have to buckle down and do some work. And I didn't know at the time I had dyslexia. I hated numbers. I hated fractions. Nothing ever made sense in my brain. I couldn't see like what my friends saw. And they were just able to turn that crank and it just worked for them every single time. I'd turn the crank and I'd get 3 different answers. And but it did start me along a path of like, no, I'm going to prove her wrong. I spent the rest of my education proving her wrong. My origin story, right? Okay. So yeah. All right. Not sure why I told you that story, but there you go. 1 over 15 minus 1 over a positive 15, positive 25 inverted gives me an image distance of 37.5. So, by the way, if you put centimeters in, you get centimeters out. I don't know if you noticed, but everything's been in centimeters. Watch out in your homework. They'll probably give you like a focal length in centimeters and then tell you the object is 1.2 meters away. What do you have to do? Just get them all in the same unit. Doesn't matter which one it is, right? Just make sure you get probably centimeters because they'll probably want the answer in centimeters. We tend to use centimeters in optics because we tend to be talking about smaller systems, even in telescopes. So this came out positive. Ooh, okay. What does a positive image distance mean? It's on the back side. This is different from mirrors, right? Where positive means it ends up on the same side. For a lens, positive means it ends up on the opposite side. So just, again, easy traps to fall into, right? Have this in front of you at all times when you are working these things, right? Don't think that you know. Okay? Always check. Always look at it. I'm constantly doing this, right? I have this picture on my computer. I'm doing optics. This is up, right? And I'm checking.
How do we know there's
Ah! How do you know the answer to that, Jamie? What's always the answer if you want to know if it's real or virtual? Look at the diagram. Look at the ray tracing. Okay? So, but we can calculate the magnification, right? Negative image distance over object distance. So that's a negative of a positive 37.5 all over a 25. Ooh, this is negative 1.5. So, upright or inverted? It's inverted because there's my sign on it. Magnified or reduced? Magnified. Real or virtual? Real. And how do you know which picture to look at? You guess. Our problem had an object distance that was bigger than the focal length. Object outside of focal length, right? If I give you another problem where I tell you that the object distance is inside the focal length, you gotta look at this picture. Because this'll work. So if this focal length is 15 and this object distance is anywhere from 14.9 to 0.1, this picture still works. Yes, the details change a little bit, like how much magnified or whatever, right? But like the point is that it's in, there's two regimes for converging lens. Outside the focal length and inside the focal length. And I had you experience it, right? The two different kinds. So let's do that example. Where now we are going to have a diverging lens. Okay? So if I tell you the focal length is 15 centimeters, what do you have to make sure that you put on that 15 centimeters? Okay? A negative focal length. It's diverge. Oh, back up. This is not what we're doing. I could just hit blank the screen, but this feels better. Okay. It's still a converging lens. Sorry. So the focal length is what? Positive or negative? Positive. Okay. It's supposed to be 15. And this time, though, I'm going to put the object at a distance of 10 centimeters. So now we're inside the focal length, right? I've got my lens right here. I've got my focal length. My object's inside. If I ran the simulation, I would get a picture that basically tells me that there's dotted lines here. Okay? So I know I'm going to end up with some sort of virtual image. So let's do the calculation. 1 over positive 15 minus 1 over 10. Negative 1. What does that give me? That gets me a negative 30 centimeters. Okay. What does a negative sign on my image distance tell me according to the conventions?
On the front.
It's on the front side, meaning the same side that the object is on. Is that what the ray tracing diagram tells me? Yes. Okay. Now when I go to calculate the magnification, am I going to get a positive or negative number? I'm going to get a positive number, so what does that mean about the orientation? It's upright. And because the number is bigger than 1, it's going to be magnified. So again, going back to that picture, right? Not that picture. That picture. That's what I've got. If I go to the simulation, I bring my object inside the focal point. You see how I crossed the focus there? Right, and now it's inside.
So the reason we really need the sketches of the different situations and relationships between object and image are just for the virtual and
Really, it's for virtual and real, but it's to orient your brain, to give your brain a visual thing to latch onto.
and we can also double check our calculations for the magnification.
Yeah, and if we're not doing it, but if I had taught you how to do like an actual ray tracing diagram, a scale diagram, like where you're measuring out with your ruler and stuff like that, your diagram would also accurately predict exactly where these things are. Yeah, we're just letting the computer do it now. Yeah, I do think it's better. It's been a long time in coming, and it took a pandemic for me to realize that we should really not be drawing.
Is this the first semester?
This is the first semester in a face-to-face class I've not done ray tracing diagrams. Like actually showed students how to make them. Yeah. So I make changes every semester.
So, no, this is virtual because it's back of
Because the lines are done.
Because the lines are done. Because that image can only form in a person's brain. Somebody looking through this lens, when you were holding this like this, okay, the light that reached your eye was made from rays that are divergent. There is no way that those 3 real rays will ever come to a point on the backside of this lens. So what did your brain do?
Make it up.
Your eyeball saw all three of those rays. Your brain said, oh, well, it came from somewhere. And where did it come from? It came from where they all met in space. And that thing was on the other side of the magnifying glass, but in reality, it was in your brain.
So technically, the math does tell us that it's virtual or not, right? When the green eye is negative, that means that it's on the other side, and
If it's a converging lens. There's too many ifs in that statement for you to get it right. The way you get it right is you look at the diagram.
There's no right away.
When you have enough experience and you're very careful and you know it's a converging lens and it's a single element system, then yes, right? But like holding all that in your head, and especially that you're new to this and you're trying to figure out mirrors and lenses at the same time, it's a recipe for disaster. Trust me, you just want to look at the picture.
The lab that we need to read manual, that's next.
No, the lab that you need to read the manual is later. Okay? Tomorrow's lab is optics. You're going to do exactly all of this. That's yours. Oh, these are the extras? Yeah. Thank you. Have a great day. I'll see you tomorrow. We will be working in the dark a little bit tomorrow. Just to warn you. Yeah.